All right, here's our wave review. Number 1 says describe the displacement of energy and matter due to oscillatory motion. So we're looking at how the displacement of energy and matter change or are affected when a wave moves. So oscillatory motion meaning up and down, left and right. We've talked before about how waves transfer energy. They do not transfer the matter. So the wave energy can move left to right. The matter can move a little bit, but the matter isn't actually transferring. So letter A, answer choice A, says repeating displacement of energy, which can happen, and matter. Okay, the matter is not transferring. B says a single displacement of energy and matter. Again, with the matter doesn't transfer. C says a repeating displacement of energy, but not the matter. D says repeating displacement of matter. Again, matter doesn't move or isn't transferred. E says a single displacement of energy, but not matter. So a single displacement versus a repeating displacement. If I'm talking about oscillatory motion, I'm talking about up and down, that is repeating displacement. So answer choice C. Number 2, what is the relationship between frequency and energy related to the EM wave? So as we move from left to right on the electromagnetic spectrum, our frequency increases. So as we go from radio all the way to gamma, we have a higher frequency in gamma rays compared to low frequency in radio waves. And with the higher frequency comes a lot of energy. Gamma waves have the most energy, so there is a direct relationship between frequency and energy. What is the frequency of a wave that vibrates up and down 10 times in 3.5 seconds? So when we're talking about frequency, we're talking about the number of waves over time. And if I've got 10 waves in 3.5 seconds, I've got 10 divided by 3.5, and that gives me 2.86 hertz. Number 4, what is the period of a beach wave if 3 crests and troughs pass in 6 seconds? So period is the inverse of frequency, so it's time divided by the number of waves. So here I've got a time of 6 seconds, and the number of waves is 3 crests. 6 divided by 3 is 2, so the period is 2 seconds. Number 5, what is the period of the wave with a frequency of 6 hertz? So we're talking about period, and I'm given the frequency. Well, we know that period and frequency are inversely related. So if I want to find period, all I have to do is take the inverse of the frequency. So my period is the inverse of 6, which is 0.17 seconds. Number 6, a sound wave and a beam of light originate from the same location and at the same time. Along the way, both waves pass through an area of intense heat. Which of the following statements correctly describe their path? So electromagnetic waves like light is not affected by heat, temperature. Okay? So any of these answers that talks about how light is increasing or decreasing due to temperature, we can cross those out. Sound, however, does become affected by temperature, and as the temperature of air or water increases, the molecules become more excited, they move around faster, which means that sound can travel faster through warmer mediums. Best answer for that would be answer choice D. The light beam reaches its destination first because we know light travels significantly faster than sound, even though the light does not change speed. So the light is not going to be affected by temperature, it's going to maintain that constant speed. Sound speed is going to increase as the temperature becomes hotter or higher. Number 7, if you had an urgent message to send to a friend in the room next door, which would be the best method to transfer the message quickly and with the least energy lost? Well, think of this, or to answer this, you've got to be familiar with how sound is affected by medium or the matter. So as matter or medium goes from a gas to a liquid to solid, the particles get closer together, and sound vibrations can transfer a lot quicker. So the best answer for this would be D, because the sound is traveling through a solid rather than any other method. Okay, number 8. Amplitude is a measure of any wave's what? Well, we know amplitude measures the height in a transverse wave, and amplitude measures the density in a longitudinal wave. But to describe amplitude to relate to both of those types of waves, the best answer would be D. So a higher amplitude means that there's more energy in that wave. A lower amplitude means that there's less energy. So the higher my transverse wave, the more energy it has. The more dense my longitudinal wave the more energy it has. Number 9. If the International Space Station exploded, how long would it take for the sound of the explosion to reach the Earth's surface? Well, sound doesn't really travel in space. So there will be no sound heard because sound doesn't travel in a vacuum. So sound doesn't travel in a vacuum. All right, number 10, if the International Space Station exploded, how long would it take for the sight, so we're talking about light, of the explosion to reach the Earth's surface? 250,000 meters below. Okay, well, I'm given the distance, and I know light is my velocity, which is 3e8. And I want to know how long it's going to take, so I want to solve for time. So velocity equals distance divided by time. If my velocity is 3e8, my distance is 250,000 divided by t. So now all I have to do is set up a fraction on the left, and I can cross multiply 3e8 times t and 1 times 250,000. And when I do that, I get 3e8 times t equals 250,000. And my last step is to divide both sides by the speed of light. These will cancel, leaving me with a time of, let me scoot this over here, a time of 8.3 times 10 to the negative 4 seconds. That's my velocity. I'm sorry, my time. Number 11, alarm clock and a light bulb were placed in a vacuum chamber. Which statement below is true regarding the scenario? Well, I know that light can travel in a vacuum. Sound cannot, because sound needs a medium to travel through. So I'll be able to see the alarm clock, I'll be able to see the light, but I will not be able to hear the clock because there's no matter to travel through once we create the vacuum. Answer choice D. Number 12, as the frequency of an electromagnetic wave increases, select all that apply. Well, as the frequency increases, so the waves get closer together, the wavelength gets shorter. Now the speed of the waves doesn't change because all of the electromagnetic waves travel at the same speed. Number 13, which set of waves is in order of increasing frequency? Okay, well, for this you got to think about your electromagnetic spectrum like the one that's on page 6. From left to right, you got radio on the far left, you've got gamma rays on the far right with the highest frequency. So gamma is going to be the highest frequency. It's certainly not going to start off. Radio is on my far left of the spectrum. Then we've got infrared. And then yellow and purple. Is it purple and yellow or yellow and purple? Well, in the visible spectrum, it's Roy G. Biv. Red, orange, yellow, blue, green, indigo, violet. Violet being purple. And then X-rays. The best answer here is answer choice C. Number 14, destructive interference occurs when? So destructive, they're going to destroy each other. They're going to cancel each other out. So it's got to be a crest and a trough. So it's not A, it's not C. And when they cancel each other out, you get areas of no energy. In a standing wave, those are called nodes. Answer choice B. In number 15, we're talking about constructive interference, where they're going to come together and form a larger wave. So I know it's not B, because I just answered that in 14. And it's not D, because that's destructive interference. I know it's not A, because the nodes are referring to destructive interference. Through process of elimination, I'm looking at answer choice C, because two crests or two troughs, when they collide with each other, they're going to form a larger wave. We call those antinodes in a standing wave. Number 16. After wave pulses interfere, so in other words, when a crest and a trough combines, what do? Do they remain stuck together? Do they reflect off one another? Do they pass through one another? The larger wave takes over? No. The best answer is that they form one larger wave or smaller wave, and then they continue moving in their original directions. Answer choice C. Okay, so here on number 17, we are looking at a wave that's got these dense, very dense regions here, 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 and least dense regions in between here. So looking at this wave, I know that this wave is a compressional wave, also known as a longitudinal wave. So it's not A, it's not B. And I know that in a compressional wave, the medium travels parallel to the energy. So the energy is going to move left and right. The medium is also going to move left to right. They're in the same directions. They're never going to intersect each other. So the best answer here is C. Number 18, how many waves are shown? Okay, well this picture is can be a little difficult to look at, but let's look at it. Well, here I've got the beginning of one compression. Here we've got the beginning of the next, so that's one wave. Beginning of the next, that's two waves. So we've got a wave here, we've got a wave here. To the next one, that is also another wave. So I've got three full waves. Yes, there is a little portion here. I'm not too concerned about how much of a wave this is, so all I'm going to say is that there are at least three full waves. What is the length of the wavelength of the waves? Okay, well, let's look. Here it's measuring from the beginning of a compression to the beginning of the next compression, and it's marked and labeled 5 meters. So the length of one wave is 5 meters. What is the length of the compression? So the high dense areas of my longitudinal wave. So the more dense this is, the greater the amplitude, the greater the sound may be. This shows me a length of 0.5 meters. Number 21, what is the length of the rarefaction? That's the least dense areas of my wave. That's this little section right here, labeled 4.5. And if I add up the length of my rarefaction plus the length of my compression, 4.5 plus 0.5 gives me 5, the length of one full wave. Number 22, the wave shown below, that's this wave down here, is opposite of the one that we just looked at. So I know this is not a compressional wave. This wave looks like a little snake. These are transverse waves. So the medium goes up and down, but the energy goes left to right. That is a perpendicular direction. Answer choice B. How many waves are shown above? Okay, well, this should be below. And if I start here, go up, up, that's one wave. Up, that's two waves. Up, that's three full waves. And then there's a little part right here that's about half of a wave. Okay, so I'm going to say 3.5 waves. 3 full waves and then half of a wave. Number 24, what is the length of the wave? Okay, so here it's measuring from this point to this point, which is showing me one wavelength, and that is giving me a reading of 1.5 meters. Number 25, what is the length of the trough of a wave? So if I look at the length of the trough, I know it's going to be comparable to the length of a crest. And from here to here, showing me a length of 0.75. So I will say the length of the trough is 0.75 meters. Okay, again, same answer for crest. The length of the crest and trough should be the same. What is the length of the amplitude? Amplitude measures the height of the wave from the equilibrium line. This value shows me the height from the crest all the way down to the trough. But I need to measure from the equilibrium line to a crest or trough, which should be half of this height. If this is 1, half of that should be 0.5, which is indicated right here. Okay. Number 28. A spring bounces back and forth 10 times in a minute. So it's got 10 cycles in 60 seconds. What is the frequency? So we want to know what F is. So remember, frequency is cycles over time. If the cycles are 10, and we're in 60 seconds, 10 divided by 60 is going to give me 0.17 hertz. Number 29, the distance between the compressions is about 0.5 meters. What is the speed of the spring's oscillations? Let's go ahead and cancel this one out. I don't want to work on this one. We'll skip it. Number 30, how far away is an ambulance if it takes 0.75 seconds time to hear the siren? So we're hearing it, so that means the speed of sound is 343 meters per second. I want to know how far it is. That's distance. So if velocity equals distance divided by time, my velocity is 343. My distance is unknown. My time is 0.75. We're going to set up a fraction on the left so that we may cross multiply. And when I cross multiply the 343 with 0.75, I get 2.25 times 10 to the 8th meters. Number 31, which choice below correctly describes properties of light waves? Well, in class, I recommended that we cross out mechanical for answer choice C and make it electromagnetic. Okay, and our answer is C, because in electromagnetic waves, they travel slower in dense mediums. So as they go from a vacuum to a gas to a liquid to a solid, they slow down. And they travel through space because there would be no medium to slow the energy. Okay, best answer C. 32, which choice correctly describes sound waves? Well, sound waves are mechanical waves, so they're not B. And these waves travel faster in dense mediums. They cannot travel through outer space or a vacuum because there's no medium to carry the energy. Answer choice A. And the last three, how many standing waves are shown below? Okay, well, remember, if I can count the antinodes, the big areas here, then I know how many waves there are. Well, here's one antinode, here's two antinodes, here's three antinodes, four antinodes. So this answers number 35, 4. Antinodes are areas of constructive interference where two crests or two troughs collide, forming a larger wave. Therefore, there are 4 waves in here. because each antinode has a crest and a trough. So that's one wave. Crest and a trough, that's 2. Crest and a trough, that's 3. Crest and a trough, that's 4. And the nodes are always the number of antinodes plus 1. Areas of destructive interference. Areas where there's no energy, no wave. There's one here, one here, one here, one here, and one here. That's 1, 2, 3, 4, 5. 4 plus 1 gives us 5.